Hello, and welcome to the most unique programming idea on YouTube, creating a chess engine and artificial intelligence to play using it. This has never actually been done before. Okay, fine, so maybe it's not the most original idea, but hey, I like chess. Sue me. Please do not actually sue me. I do not have very much money and I am very small. Now then, what are we actually going to do in this video? Well, to make a chess AI, we have to make, chess. So to do this, we're using C++ and SDL, which stands for Simple Direct Media Layer, and SDL is a cross-platform development and graphics designed to provide low-level access to audio, keyboard. It is used to make video playback software, emulators, works natively with C++, and there are bindings to several other languages, including C# and Python. Sorry about that. So basically SDL is just an easy way for us to make graphics windows, and to draw textures and rectangles and all sorts of fun stuff inside them. And eventually we can use it to write images, the screen, and write text, but let's not get too far ahead of ourselves. I don't even know if this is going to work out as it is. Now, this is not going to be a tutorial. I will not be stepping through every single thing that is in my code. This will be more of you coming along with me on an adventure. We're going to make this chess program together, and then we will cry because my code is so very bad and poorly structured. However, if you want to be naughty,
you naughty, you teasing me, you naughty.
I will provide a link to the GitHub in the description where you can see and fork the code that I've created for this. In this first video, we will be creating the chess engine, so like the chessboard, all the pieces on it, and then the functionality to move those pieces. We'll also be implementing checks, checkmates, castling, en passant, promoting pieces, all the fun stuff in chess. That's a little bit difficult to do. So, as Philip Franco always says, let's just jump into it. So the only annoying thing about SDL is there's always a fair amount of boilerplate code to start off and create a window. However, the not annoying part is that I've written that code for previous projects, so I can just kind of yoink, and we're done. Now we have a window that we can resize and move around. Yay. Okay, so now we need to make a chessboard display in this window. So there's actually a few different approaches to this. I could create an image of a chessboard in Photoshop and just load that in. But I don't like that method because it locks me into using a certain color scheme. So let's generate our board on the fly instead. Let's talk math for a second. If we have an 8x8 board, we can assign each row and column a number, starting at 0 because reasons. And if we add the numbers of each row and column, each square is going to get a value. Now I'm going to let you pause the video and see if you can figure out the pattern. It's pretty simple. So as you can see, if we highlight all the even squares green and all the odd squares red, every other square is even/odd. So this means that with a simple bit of math, namely the modulus operation, we can figure out what square should be white and what square should be black. So we just loop over each square, and if the row plus column is even, we'll paint it white, and if it's odd, we'll paint it black. Or is it the other way around? Oh well, we'll figure it out. And look at that, we have a chessboard displayed. Kind of. It's a bit small right now because I'm arbitrarily assigning the widths and heights of the boxes, so let's make those sizes based on the window instead. Amazing. But now we just have the teensy weensy tiny issue that resizing the window doesn't work at all whatsoever. Let's write some code to fix that. It should be as simple as some algebra and calling a resize function whenever SDL tells us that the screen was resized. And just like always, it functions perfectly on the first try. Okay, something went wrong here. Let's try to fix that. And there we go. So we now have a chessboard that's centered within the window, and we can also set the colors to whatever we want. We're probably going to change them a bit later, but for now, let's mush forward. Let's talk chess pieces. There are 6 of them in total. We have the scrawny pawnies, the wily knights, the ferocious rooks, the loathsome bishops, the weak king, and the mega queen. And of course, these pieces come in 2 shades, white and black. All these pieces can move in fun different ways, and if you want to know what those ways are, please go to this cool website called https://www.google.com. So this brings us to our first major decision we need to make. How do we want to represent pieces in our game? We could create some complex object, we could use characters or strings, or we could use something much simpler. So let's talk binary. Binary is just a bunch of bits that are either ones or zeros. If you put a string of these ones and zeros together, you get a byte, which is 8 bits. We can do operation on these bytes such as ands or ors. A binary and is just an ampersand, and a binary or is just a pipe, or this straight line. For the and operation, we compare 2 bits, and if they're both 1, then the result is a 1. Otherwise, the result is a 0. Pretty simple. For the OR operation, we compare 2 bits, and if they're both 0, then the result is 0, but if at least one of them is a 1, then the result is a 1. There are other, more complex operations, but we won't be needing them. And we can also do this with more than 1 bit at a time. So back to chess. We have 6 different piece types, and 2 different color types. If we use 8 bits, we can set one of the first 6 bits to 1, depending on the piece type, and one of the last 2 bits depending on the color. So for a white pawn, we would set the first bit to 1, and the last bit to 1. For a black rook, we would set the second bit to 1, and the second to last bit to a 1. And here are all the different piece types and their corresponding codes. Note that this is not the only way to do this, and probably not the best way, but it's the way we're going to do because I am lazy and this seemed easy. It's very easy now, given 8 bits, to tell what piece and color it is. If we want to tell if a piece is white, all we need to do is binary and it with white, and if the result is white, then we know that the piece is white because there's a 1 in the position where there should be. The same tactic works to tell if a piece is a bishop, a king, a queen, or whatever. Okay, I am boring myself now. I apologize for that likely too long an explanation, just to tell you that we will be representing the board by using a 2D array of unsigned 1-byte integers, or a uint8 in C. Now I know the next thing you're wondering is, Jacob, these pieces you've been showing all look so great. Where did you steal them from? Well, I'll have you know, thank you very much, that I made all of these pieces myself, from scratch, the last time I tried and miserably failed to make chess. So, all we need to do now to display our pieces on the board is to load in our textures and to tell our program to display each corresponding texture in each board space depending on what the unsigned 8-bit integer in that corresponding space is. So if we fill our board with the byte that represents a black knight, we get this.
"'Tis but a scratch."
So that looks like it's working great, so let's talk about Fen Notation now. Fen Notation is just a way of representing a chessboard. It looks like this. This represents the starting position of a game of chess. It's a little confusing at first, but it's very easy to read once you understand it. Fen Notation has 5 fields. The first is all these letters and numbers, which represents all the pieces and their locations. It starts at the top row of the chessboard, and each slash represents a new row. The letters represent pieces as follows: R for rook, N for knight, B for bishop, Q for queen, and K for king. If the letter is lowercase, that means it's a black piece, and uppercase means it's white. If you ever see a number, that means that there are that many blank spaces at that spot. This is why there are 4 8s in the middle of this starting position, because the chess game starts with 4 empty rows in the middle of the board. But it's also possible to get a row that looks like this. This is read as 4 empty spaces, then a black pawn, then 2 empty spaces, then a black king. Alright, the second field is just whoever's turn it currently is, W for white, B for black. The third field represents castling availability. If there's a K, it means kingside castling is available, and if there's a Q, it means queenside is available. Again, uppercase and lowercase is for white and black respectively. The next field is the square that can be moved onto with en passant. If there's no square, which means the last move is not upon moving 2 squares, then there's just a dash. And the last 2 fields are just related to how many moves have been made, so we won't really worry about them. So I'm going to program my chess engine to be able to read in positions based on this notation. Alright, so we're trying to read in the starting position, and it works on the first try, just like always. Alright, a few bug fixes later, and wow, it's finally working. As long as you want to play a game without rooks. Okay, last try, here we go. And look at that, the board is finally loaded in correctly. Note that we can't pick up and move any pieces around. This is very sad. We'll fix this now. This part is actually very easy. All we need to do is listen for mouse presses and then check which square the mouse was clicked on. Then once we know which piece was picked up, we can draw that piece onto the mouse so the player can drag it around. Obviously there's some hinky stuff that can go on, like you don't want players to be able to move their opponent's pieces, but we'll just shove that into our code while we get the mouse situation under control. Alright, so we can kind of click and move pieces, but we can't place them down. Now we can click and move pieces and hold them in the middle. See how realistic this is? Computers are so awesome. But we still can't put them back down on the board. Let me just slam together a slimy little function to place the piece that the player is currently holding onto the board, and remove the piece from the square it is being dragged from. Alright, so we have some weird version of chess where you can clone your own pieces. I don't really want that though, so give me a second. And boom, we're able to move pieces around, and it all looks great. You can see that we're only making legal moves, so I guess we're done with this project. And... oh. Oh no. Oh no. So in chess, apparently moving any piece to any board square is not a good way to play. So we're going to have to figure out whether a move is legal or not. The coding process for this part will be plain in the top right while I'm talking because this took a freaking long time to implement. I'm going to need to differentiate between pseudo-legal moves and legal moves here. A pseudo-legal move is any move that can be made on a board based on how the pieces move. For example, you could castle, you can move a bishop diagonally, you can move a knight in an L shape. If it's a pawn in its starting position, it can move forward 2 spaces or 1. Those are all pseudo-legal moves. To generate all these, we just go through every piece and check what moves it can make based on the empty squares of the board, and add those moves onto a list of pseudo-legal moves. Then, at least for now, all we need to do to see if a move that the player is trying to make is legal is to check if it's in that list. If it is, then the move is pseudo-legal. I also decided to highlight the possible moves to make it a bit more intuitive, and this actually worked out pretty well. We're able to make all the pseudo-legal moves that we want, except promoting, but don't worry about that, we'll definitely remember to do that later.
Sometimes foreshadowing is relatively obvious.
Now the issue with just using pseudo-legal moves is that it completely ignores checks and checkmates. For example, if we played using just these rules, this would totally be legal. Because we live in a society that has rules and standards, this is not acceptable. If you want to not care about your royalty, just move to France. Creating a list of legal moves isn't actually that hard. We just need to go through every pseudo-legal move and see if it would result in your king being in check. If it doesn't, then we add that move to the list of legal moves. Otherwise, we toss it in the trash. It's at this point that we'll also have to care about some annoying castling rules, such as you can't castle if your king is attacked, and you also can't castle through check. But Jacob, I hear you asking, how can you tell if your king would be in check after a move that hasn't even happened yet? Well, that's a stupid question, and you should feel stupid for asking it. Close this video right now. Go on, I'm waiting. Okay, now that they're gone, the way that we tell if a king would be in check after a move is we make a copy of the current board state, and then we just make the move. Then we switch the turns and we check if any of the other players' pieces can take the king. If there is a move that would take the king, then the initial move is not legal, so we just don't add it to the list. Boom. Easy. Now you see why I had to kick that other guy out. It's just way too simple and intuitive, and I definitely didn't spend an hour implementing it, and it's definitely not the slowest part of my entire program that I'll need to fix in the next video. Alright, after doing a lot of refactoring and fiddling around with my code, I actually have it kind of working, so let's take a look. Okay, so I think it's working, but I'd really like to know for sure that it's working. So let's do some verification. So do you remember that part of the beginning where I said no one has ever thought of programming chess before? Yeah, that was kind of a lie. The first chess program was developed way back in the dark days of 1956, before they even had indoor plumbing. Had some good priorities. In fact, it's so much of a lie that there's an entire chess programming wiki dedicated to programming chess. In this wiki, they have documented difficult chess positions and how many new positions can be reached in 1, 2, 3, 4, 5, even 6 moves. This is something we can calculate as well, just by making every single legal move, and then making every single legal move that results from those moves, and so on and so forth. I don't really understand it myself either, but let's just do it. You can see the total amount of future board positions in the nodes column. So from the starting position, there are 20 possible positions after move 1, 400 after move 2, 8,902 after move 3, and so on. So for my program, we will just check the first 4 moves from the starting position, because my computer will literally crap the bed if I try to go further, because I've programmed this system very poorly. And sick, the amount of positions matches up. That's a great sign. Let's try some more weird positions that chess programmers have noticed can expose a lot of bugs, starting with position 2. And it's wrong. So I'm finding 77 more positions than I should be finding. Damn. Debugging time. Aha! So you remember when I said that I would remember to do promotions? Yeah, well it turns out I totally forgot to do that. So let's program that in now. Alright, promotions are looking great. And just for fun, let's make it so we can make random moves happen to see the promotions happen in style. This will be our first pseudo bot. Okay, so now that promotions are done, hopefully we'll get the right amount of positions when we verify our code. And it's still off. Okay, more debugging time. Ah, okay, I figured out one of the bugs. Remember when I said that you can't castle through check? Well, the way that I see if a square is attacked is I look if an enemy piece can move to that square. But the issue with that is that pawns move differently than they attack. So I can castle through a pawn attack easy peasy, which shouldn't be possible at all. Let's fix that. Alright, we fixed that bug, so now we should generate the right amount of positions. Come on, no whammies, no whammies, no whammies! Damn it. Okay, we're still off, but by 41 this time. So that's nice. I'll be back. Okay, this better be the final bug. So right now when I check if the king can castle, apparently I'm not checking to make sure every square between the rook and the king are empty. So you can do this sneaky little maneuver. Yeah, I swear I've played chess before. Okay, last try and then I'm throwing my computer out my window. Hell yeah, we got the right amount. And it only took 8 minutes to calculate 4 moves ahead. I'm finally satisfied that our chess engine is complete. Now let's enjoy the fruits of our labor a little and play some chess. Alright, so that's going to finish it off for this video. For next time, do you remember how calculating only 4 moves ahead literally took 8 minutes? Yeah, that's way too long. So we're going to optimize that, and then we're going to make some AIs that will hopefully be able to beat me. So please, drop a like if you enjoyed this video, I had a lot of fun making it, and subscribe if you're interested in seeing some more coding content. Have a groovy day!